There are three basic problems in a hidden Markov model. For simplicity, we are going to use the coin flip example, but later on in the bioinformatics application section, you can see how this is being used in real problems. The three problems in hidden Markov model, the first one is, given that the parameters for the hidden Markov models are all provided, how do we compute the likelihood of a particular observation? For example, if we know there is a fair coin, bias coin, if we know the initial probability and transition probability and emission probability, can we calculate the probability of seeing a string of coin flips, such as head, tail, tail, head, 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 tail? And so for that, there are two computational procedures that can achieve this answer. But first, let's think about how we want to solve this problem. So let me remind you again the initial probability, transition probability of this hidden Markov model. So supposedly, we know the state sequence. If the observation is this, and if we know that the coins that are used underneath each coin flip is the following, FF, bias, and so on. We can easily calculate this based on the transition probability. From a fair coin to get to a head is 50%. A fair coin to a tail is 50%. Bias coin to get a tail is 20%. And bias coin to get a head is 80%, right? So very easy, you can calculate this. If I give you another coin, like a string of coin order, which have these two coins changed, we can calculate the probability again, which will give you a different result from the path above, but it's a very easy calculation. So you can see, given each path, you can easily calculate the probability using the emission probability of the two coins. Then the question is, what is the probability of seeing this path? Let's look at the first path. In order to use this particular order of coins, we say, oh, well, first we have to pick a fair coin. So that's the initial probability of 0.4. But also we have a transition probability from a fair coin to another fair coin, from the fair to bias, bias to fair, fair to fair, fair to bias, bias to bias. And so that you check the transition probability, and you can calculate this quite easily. If now look at the second path that we're given, again, we have to start using this bias coin. That's from the initial probability. And then after that, you just check the transition probability from one coin to the next. You can calculate this probability. And so you can see here, it's also fairly easy. Every given path has its own probability of occurring, knowing the hidden Markov model parameters. Therefore, the probability of seeing this particular coin flip order is to sum over all the possible paths. Every path has its own probability of happening, multiplied by the probability that on this path, you are going to give out this particular coin flip, right? So you can see written as this is the probability of a particular path given the hidden Markov model parameter. And with the parameter, with that particular path, what is the probability that this path will give out this particular coin flip? But you have to sum over all the possible paths, right? So you can imagine for a path with n long, so n number of events in here, and the t number of hidden states. In our case, the hidden states are fair coin and bias coin. There are 2 to the n possible paths. And so imagine if the t is high and n is also long, say stock market, you are looking at a year, there's only bear and bull market, 2 to the 365 days. It's an unfeasible calculation. That's why you need a better computational algorithm to solve this problem. And for that, we use dynamic programming. Dynamic programming is an approach that we can keep the previous subproblem solution in order to speed up the current calculation. And so in this situation, we try to keep track of all the numbers we get from the previous step, because at every time point, we have to calculate probability, and we'll show you how you can keep track of the previous step's result in order to help you with the next step of result. This way, we don't have to enumerate all the possible paths in order to calculate the final probability. So let me show you the first approach, which is called the forward procedure. Again, we have this particular coin flip, and we want to see, what is the likelihood this is going to happen. And so you initialize like this. We ask, what is the probability of seeing a head from the fair coin or biased coin? And so let's just calculate one at a time. You can see here, this is let's use this red circle here to indicate the probability of using a fair coin in order to get this head. This is calculated as we have to pick a fair coin in the first place, which is the initial probability of picking a fair coin. And then from that fair coin, we have to emit a head from the fair coin emission probability. We can calculate the same for the other side, which is a number we keep track of in this yellow circle here. If we use a biased coin, initial probability is biased coin, and the emission probability from the biased coin to give out this head. And so that's, here, initial probability times transition probability. And you keep track of these two numbers, and we call them alpha. So the alpha 1 is the probability of seeing a head using a fair coin at this first position. The alpha 1b is the probability of using biased coin to get this head in the first position. And now we look at the next step. So again, we say alpha actually is now keeping track of the probability of seeing a particular coin flip at this location, and all the numbers before, all the possible coin flip before. Let's look at this particular coin flip. At the second coin, we ask, what is the probability that we are getting this T and also the previous H if we're using a fair coin? We say, well, what are the possibilities? In the previous coin, we could use a fair coin, but transition from the fair coin to a biased coin, or we can use the biased coin and transition to a fair coin. And so, and both are possible. So we just add up their probabilities together. In this case, it would be, it would be this alpha, this yellow number stored in here, multiplied by the transition probability from a fair coin to a fair coin, plus this probability of previous coin using bias to get this head, multiplied by the transition probability from the bias coin to a fair coin. And so when we sum these together, we know that now we are on the fair coin, but also from here, we need to emit a tail using this fair coin. So we multiply this, the sum of these two numbers by the emission probability here. And we can do the same thing for this other side. What's the probability of using a biased coin in order to get a tail here and everything before? And we say, okay, well, we know that in order to get anything before, if that previous coin was coming from a fair coin, That's the probability. We multiply by this yellow number here, the alpha number here, by the transition probability from the fair coin to the bias coin. The other option is, to come from the bias coin, and we inherit this yellow alpha number here from the bias coin here, and then transition from bias to bias coin. That's the transition probability. We sum this together, and so now we know we are using a bias coin. But using this coin, there is also a emission probability of giving out a tail from the bias coin. And so if you convert that into the probability calculation, you can see here, we inherit the previous number here, multiply by the transition probability, and sum by this number, and then multiply by the transition probability, and we sum them together, and then from the fair coin we emit the head, right? And then so on. And so you can see at every step we calculate the summation of the previous and use the results from the previous step. And now if we continue this calculation, we ask, what is the probability that in the third coin, I'm going to get a T if I use a fair coin? We say, okay, well, if you use a fair coin now, well, what's the probability that the previous coin is a fair coin? Well, if the previous coin is a fair coin, in order to get anything before that, this is the probability we already calculated. But then we have to transition from this fair coin to the fair coin. So that's multiplied by the transition probability. Alternatively, the previous coin could be a bias coin. And then we'll inherit this number, which calculates the probability of using a bias coin to get all the coin flips before, multiplied by the transition probability from a bias coin to a fair coin. And we add up these two numbers together. Now we are in the fair coin, and then we have to emit the tail from this fair coin, right? Or you can calculate the probability of emitting the same tail and everything before using the bias coin here. Again, there are two options. You either inherit this number, multiply by the transition, or you inherit in the previous coin being biased, and you do the bias to bias transition. You sum them up, and then at this bias coin, you emit the tail. And so you can see here, the calculation is much easier. At every step, we trust that the previous number was calculated correctly, and we just inherit this number to help us calculate the next step, and so on. And so, yeah, same thing here, like this. And so now if you think about if the string of coin flip is very, very long, like 300 long, instead of calculating all 2 to the 300 times, 2 to the power of 300, at every step, we only just inherit the previous two numbers. And it's kind of almost linear to the path you have, right? So it's if you have n states, n time points and the t different states, it will only be n times t. So it's a much more manageable calculation, very, very fast. At the very end, if we reach the end of the 3000, we say, well, what is the final probability of observing this particular string of coin flip? Supposedly we only end at 4. You say, well, at the end, I just need to make sure that the probability of getting all the coin flips are already here, and the final coin flip I'm getting ahead, but that can come either from the fair coin or coming from the bias coin. And so I just add two numbers together, and then I'm done. So you add the final two numbers, you will get the probability of that particular coin, the particular order of coin toss you observed. So that's the forward procedure.